Dear students, welcome to another episode of Statistical Physics I. Today we will study about the binomial distribution applied to a magnetic array. So last time we studied random walk in one dimension, and from that one dimension we concluded that it has somehow some resemblance to binomial distribution, and the binomial distribution actually is p plus q raised to the power n equals it can be written in this fashion. Here we last time showed that p is the probability of moving to right, q was the probability of a hypothetical cat to the left, and n1 was the number of steps to the right, and n2 were the steps to the left. So आज हम इसी कंसेप्ट को अप्लाई करेंगे, लेकिन टू अ डिफरेंट सिस्टम, और देखेंगे कि बाइनॉमियल डिस्ट्रीब्यूशन की एप्लीकेशन कैसे हो सकती है उस सिस्टम पे। तो उस सिस्टम को समझने के लिए आपको पहले ये समझना होगा कि हम स्पिन कंसिडर करते हैं। इन क्वांटम मैकेनिक्स यू हैव हर्ड अबाउट द spin of an electron or spin of an atom overall. So basically spin is such an entity which interacts with magnetic field. Spin is a property of a particle with which we estimate or we somehow quantify the interaction of the particle with an external magnetic field or the interaction with its neighboring spins. सो ये चीज़ तो आपने क्वांटम मैकेनिक्स में सीखी है, ये यहाँ पे आपको सिखाने की ज़रूरत नहीं है। जस्ट यहाँ पे ये है कि हमारा अब वास्ता जो है वो स्पिन से पढ़ने वाला है। तो हम एज्यूम करते हैं, हमारा जो टॉपिक है वो यहाँ से स्टार्ट लेगा। एज्यूम देयर आर first we assume there is a lattice. Assume there is a lattice one dimension in one dimension on which representing atoms. Okay, lattice किस चीज़ की है? It represents atoms in सॉलिड और तो सॉलिड्स में एटम जो हैं वो एक ख़ास तरतीब में होते हैं, तो हम एक इमेजिन करते हैं कि एक ख़ास तरतीब में एटम मौजूद हैं और उनके ऊपर स्पिन मौजूद हैं. सपोज वी हैव 10 such sites, 10 lattice points. Let we have 10 lattice sites on which we want to place single spins, single electrons or single atoms. Where we don't specify what we are placing, but they are actually single spin entity, single spins. So हम एक तरतीब उसकी ये हो सकती है कि one spin up, second spin down, again up. So यहाँ पे आपको ये थोड़ा सा मैं बता दूँ कि स्पिन्स की दो डायरेक्शंस ही हो सकती हैं. Spins are single spins with only two possible orientations. Either they can point up, so then we call it, this is plus m spin, and if it is down, then it is minus m. स्पिन कह दें इसको, मैग्नेटिक मोमेंट आप बोल दें इसको. इट कैन बी कॉल्ड आल्सो magnetic moment. Depends if it's a single electron or it's a nuclear spin. Here we don't specify, so it can be any of these things. So we place 10 spins in random order. So first 2 spins up, then 3 spins in the downward direction, and then again 1 spin up, then 1 again down, and then again 3 spins up, and we specify positions. So this is first, second, third, fourth, fifth, sixth, seventh, 3, 4, 9, 10. So okay, I drew one extra. So we make another assumption. So we say that these spins do not interact with one another. So normally they do. So if we place 2 spins together, they do interact with one another. लेकिन यहाँ पे हम ये suppose करेंगे कि ऐसा इंटरेक्शन नहीं है. ऐसा स्टडी करने के लिए हम करेंगे, जब हम रियल सिस्टम्स को स्टडी करेंगे तो देन हम उनकी इंटरेक्शंस भी स्टडी किया करेंगे. लेकिन यहाँ पे हमने फ़िलहाल स्टैटिस्टिकल नेचर को समझना है, तो हम इनकी इंटरेक्शन को इग्नोर करते हैं उसके तौर पे. सो 10 to study 10 spins at 10 lattice sites at from 1 to 10. So this is a little bit larger system. It is a larger system. So we start studying from somehow lower level. So initially assume that we have only 2 lattice points and 2 spins to be placed. How many arrangements are possible for such a case? We studied very well this phenomena, and we know that there are, so because there are only 2 orientations possible, one upside and one downside, so it should have how many number of available arrangements? Number of arrangements we know from our statistics knowledge that they are 2 to the power n, and in case of 2 spins only, so this is 2 to the power 2, only 4 arrangements. How many arrangements? 4 arrangements. So if we write like this, so first arrangement would be okay, both of them in upward direction. Second arrangement would be first spin up, second spin down. Third arrangement would be first spin down, third spin up, second spin up, and fourth will be both of the spins in downward direction. So these are the 4 configurations that we got from our knowledge. These 4 are here, 1, 2, 3 and 4 arrangements. So now there is an interesting analogy with the square of 2 entities. So you remember 1a plus b squared is equal to a squared plus ab plus ba plus b squared. You know this formula really well. And if you put spins instead of a and b, and we write it like this, we can write it, okay, so this is for both spins up, this is for one up, one down, this is for first down, second up, and this is for both down. So there is a similarity between these two formulas. So now instead of writing for 2 spins, when we want to study 2 spins on a lattice site, we write this formula, up spin plus down spin whole squared. So it will give us all the possible arrangements inside that thing. And if, for example, now we can if we ignore the order, then we will get, okay, 2 times this plus this. So here we have ignored the order, so we can write it as 2 times whatever, any of these 2. I write it in the parentheses when we ignore the order. So let's go to 3 spins on 3 sides. Now we have 3 lattice sides and 3 spins. How many configurations? Total number of configurations, that is 2 to the power 3. Now we should have 8 configurations. How? So I draw them in front of you, 8 configurations. So these are all 3 up, then 2 up, 1 down, like this, and there are 3 of these actually, in which 1 is down and 2 spins are up. So this should be like this, and others are 2 spins down, 1 up, and they can be arranged in 3 different ways like this. And then finally we have this everything in the down spin configuration. So these are the 8 arrangements, total number of configurations. And if we now ignore the order, they remain only these through are joined together and these through 3s are also joined together. So if we ignore order, then they are, okay, 3 like this, or 1 like, okay, so 3 spins up, and then plus 3 spins like 3 configurations in which 2 spins are up and 1 is down, and plus 3 configurations in which 2 down and 1 up, but however we write, it does not matter, and then 1 with the down configuration. And this somehow resembles now to the cube of 2 elements, cube of 2 spins. This is this whole thing. So if we keep on doing this, we will end up for n such spins for n spins on n lattice sites, we may write that total number of configurations are this thing raised to the power n. And when we write it like this for n sides and n spins, this is actually binomial function that we studied here in case of when our cat was moving to the right or to the left. So it was again p plus q to the power n. Here we have up spin plus down spin raised to the power n. So it can be written similarly in the form of binomial expansion. Just we have to change notations. So we write it like this. So it is now, look at the summation, what I am summing. So and then I will clarify what that means. N total factorial and then n up factorial times n minus n up factorial times up spin raised to the power n up times down spin raised to the power n minus n up, or you can write it like this, however you want. So these both formulas are basically they basically represent the same thing. So n factorial, n up factorial, n down factorial. So remember these subscripts. So one is n up, one is n down, and here we have spin, n up, down, and down. So this is the binomial formula. This is the binomial formula for n lattice sites in which n up number of spins are facing upwards and n down number of spins are facing downwards. So now we can even calculate the number of configurations and the probability from binomial distribution for these 10 spins very easily. But we will do some more calculations and we see what that actually stands for and what that means. So this is for one-dimensional spin array of magnetic system. So magnetic systems, any magnetic material is somehow similar to this this type of configuration. Some spins are up, some spins are down, and the overall magnetic properties of this system can be calculated when we subtract the down spins from up spins and see if there are more down spins, net down spins, or if there are more net up spins. And this we will do next. So now we define, let's define n up. So n up, we can define it somehow. So this should be n half plus s. So s is a number We call this number as spin. This is a number, an integer. And we define n down as, so why we are defining like this will be clear later. So we define n down as n half. You remember that n is the total number of spins and n half is the half of them, so n half minus s. So here we clearly define everything like this. And also we number this equation here that we wrote for the 2 spins, our equation 1, so that we don't get distracted later when we use this equation somewhere. So this equation we number as equation 1. And now we are defining n up and n down that we actually introduced here in this equation as like this. So we introduced a new constant, that is s. We call this spin, and if we add these two, we will get n up plus n down. This is basically total number of spins. And if we subtract them, n up minus n down, we get a number 2s. So okay, this we call as number 3 equation, and this we call as number 4 equation. So the difference of these two numbers, that is equal to 2s, this quantity we will call as spin excess. Spin excess means the extra spin. So if this number is positive number, we say that this is the up spins are more, and if this number is negative, we say that down spins are more. And this 2 is also somehow convenient for us in later calculations. I will show you how this is convenient, but for the time being, okay, so these both 2 equations we name them as equation 2. Okay, so these 2 equations I call them equation number 2, and this is 3 and 4. And now we proceed to our further calculations. We put equation 2 in 1. What we get out of that, we get a really cool looking formula, that is up spin plus down spin raised to the power n equals, now the summation, see now it changes from s minus n half to plus n half, because we are putting n half equal to something n half plus s, so the summation limits also change. So now we write n plus 2 plus s factorial, n plus 2 minus s factorial. We put the values as it is, as they are. So we write now up spin raised to the power n half plus s, and down spin raised to the power n half minus s, and this we call equation 5. So our equation 5 is a really interesting equation. So we could have studied this equation directly from binomial distribution of the random walk, but that was not too intuitive for us. This becomes more intuitive and more easy to study now with the introduction of a magnetic system, in which we have some spins up, some spins down, and some spin excess in it. So now if you see this formula, so this formula has 2 parts. So one is this part here, and one is the other part here. These 2 things we can call it this part. So if you remember our last lecture, the first part that we are considering here, this one, this is actually, it gives us, I introduced it in the last lecture. So it basically gives us the total number of total number of possible configurations in a binary system. Binary system means only two possibilities. So if this gives us the total number of configurations, and this is basically our formula for combinations, if you remember. This is just like the same formula as for combinations. But now we are studying our real systems, or somehow close to reality systems. Now this thing has a higher value, in conceptual value, I would say. This has a more conceptual value, and we now want to understand what this thing is actually. And this is we call this another function. We call this, let's define, n factorial over n plus n half plus s factorial into n half माइनस s factorial. इसको हम ऐसे भी लिख सकते हैं n factorial divided by n up factorial n down factorial. So we call this GNS. What we call this? We call this function, this first part of the binomial distribution of spins, we call this GNS. So we have n is the total number of moments or spins, and s is the spin of any individual. This is an integer that is helpful for our calculations. So, and we name this function Gn of s will be called multiplicity function. So you should remember now that we will always call this our multiplicity function GNS, and it would be a combination formula, n factorial divided by n plus s, or however you like it. This is our now multiplicity function, and this function is really important. This will help us in further calculations. But first we write equation 5 in terms of multiplicity function. So we defined equation 5 here, no? So we just rewrite this in terms of multiplicity function. So we get up spin plus down spin whole raised to the power n equals summation s goes from minus n half to plus n half g of ns times up spin raised to the power s down spin n half minus s. This is our equation number 6. g of s को आप और तरह से भी अंडरस्टैंड कर सकते हैं. g of ns gives us the number of states having same value of s. अगर हम स्टेट को डिफाइन करें s नंबर्स के साथ, तो जो GNS है ये हमें उस टोटल नंबर ऑफ स्टेट्स बताएगा कि जिनका सेम s होगा. इसकी डेफिनेशन भी, इसकी इंटरप्रिटेशन भी फर्दर की जाएगी कि इसका मतलब क्या है. वक्ती तौर पे आप इसको ये याद रखें कि दिस हैज़ दिस काइंड ऑफ मीनिंग. और अगर हम ये एज्यूम करें एजम्पशन हमारी ये है कि हम लेट्स हैव n इज इक्वल टू 10, और आपको भी मैं असाइनमेंट दूँ, स्मॉल असाइनमेंट. for the next, before the next lecture you have to do this. For n is equal to 10, plot a bar graph between G and S and spin axis. Then our next lecture will be very easy to understand what it will be very easy to understand what I am talking about. So now we are treating Gn of S as a function, and we are plotting it against the spin axis, that is 2s, and we want to see which type of function it looks like, how it would look like. What is your idea? This is your assignment for before next lecture, and if you will be successful in plotting these two, it is I say it's very easy. So you just need to use the formula of GNFS, which is here, this thing, and you have to plot it against spin axis, that is 2s. And then when you have this plot, we will discuss it, what that means, and we will continue from this, and we will go on to study our Gaussian distribution from that. And it's very interesting, trust me. I could have made one lecture out of everything that I'm teaching you, but it would be like very long lecture, 1.5 hours. So I stop here for the current lecture. So you just for this lecture, you know the definitions of what is Gn of S, and you have some spin system in your mind. And next time we will continue directly dealing with, we take the same spin system and we start with dealing GNS, and we see what does it mean and how it should be somehow relevant to study the Gaussian distribution. Thanks.